I'll begin with a history of charge transfer theory, very brief, of course, starting at the very beginning. So perhaps the first paper on electrochemistry, maybe not the very first, but the first on electrochemical kinetics, perhaps, was Taffel's law, or Taffel's paper in 1905, which led to the measurements for hydrogen evolution in acid, suggesting or showing a linear relationship between the log of the current and the applied overpotential, so the departure from equilibrium for that reaction. Interestingly enough, he didn't actually make a Taffel plot, which is we electrochemists plot log of current versus overpotential. He did not take a log, so that's why his curves, things are actually curved, but he drew logarithm functions and they seem to fit. In a much later paper, 2005, here's Taffel's original data scanned in from his figure and plotted on a Taffel plot. And you can see it's pretty straight, but it does curve a little bit. But it's relatively straight, and so that's Taffel's law. And that's considered sort of the starting point of modeling all electrochemical reactions. And I mentioned earlier the Butler-Volmer equation. That is the standard model in electrochemistry. I think many of you here may be familiar with it. And essentially, you could think of it as empirically formulating a Taffel's law in the forward direction, the backward direction, in such a way that the two rates kind of vanish at zero overpotential. And introducing this concept alpha, which is the charge transfer coefficient, which kind of says how much of the overpotential is biasing the forward versus the backward reactions. So that'd be the reduction versus the oxidation reaction. There are ways to derive the Butler-Volmer equation in sort of a phenomenological way from some microscopic picture, and that's really what I want to focus on today. So one way you might see it derived in some textbooks is to say, well, there's sort of if you have some reaction coordinate, which might be something like the position of an ion or maybe a bond which is being broken with some collective variable, that there's a notion of sort of the molecular configuration in the oxidized state and the reduced state. In the oxidized state, you also have some electrons, which are going to be transferred in that reaction. And when the system is in equilibrium, there's a certain sort of landscape of chemical potential, or of energy, basically, that you would have to go over that is sort of thought of as coming from short-range molecular forces. And then there's a voltage drop across the interface, which can be varied as you change the potential of the metal, or you could kind of think as like applying a linear potential profile or a constant electric field, which is sort of biasing the charge to go one way or the other. And as you sort of tilt, add sort of that linear contribution to the original sort of chemical thing, as long as this barrier is kind of staying in the same place and you don't have too big of a tilt, you can derive this Butler-Volmer equation. And the alpha essentially is telling you sort of where is the barrier in the reaction coordinates, or how symmetrically is it placed, okay? So it's kind of a reasonable picture. On the other hand, it has some problems as well. Well, for one thing, if you tilt very much, at some point there's no barrier anymore, so how are you going to use classical transition state theory? So that's a bit of an issue. But maybe more fundamentally is that at least this framework here doesn't predict anything, actually. It gives you a functional form that you can fit to data. The prefactor I0 is called the exchange current. Alpha, I mentioned, is the charge transfer coefficient. And so those parameters are not predicted, I should say. They have to be fitted to experiment. Also, if you kind of dig into it, electrochemists will tell you Butler-Volmer fits a lot of experimental data. And it does, but if you kind of dig in, you realize a lot of times it's with other empirical tweaks. The actual raw data doesn't fit Butler-Volmer, but you have to sort of fit various series resistances and other tricks to kind of get it to fit Butler-Volmer. So this, I would argue, it doesn't necessarily fit always data that well. But maybe the most fundamental thing is it neglects quantum mechanics. And after all, we're talking about electrochemistry. Electrons are quantum things, and there's no quantum mechanics here at all. So this can't be a complete picture. Now, as I was digging into this field, I was really amazed to find this paper, which I encourage you to take a look at, of Gurnie. I believe this is actually the first paper on quantum theory in electrochemistry. In fact, this guy Gurnie actually wrote one of the first textbooks on quantum mechanics, I think, in 1928. And this paper is 1931. And this paper is really very far ahead of its time. Actually, here he wrote the rate as a sum of basically some fundamental rate, which he didn't have quite right. I'll come back to that. For an electron that has energy E and an overpotential V here that's applied, or a potential V to the electrode. But he has the integral over the Fermi distribution and the density of electronic states. So he's got, like, even the solid state physics is all there. as was later developed, really decades later, actually, by other scientists I'll be talking about. But what I want to focus on is actually this picture, which is in Butler's 1936 paper, which kind of builds on Gurnie's. And this is specifically for the example of hydrogen evolution, where we're taking a proton from solution, moving it to the surface, and it's getting reduced to become a hydrogen atom, which will then meet another hydrogen atom and go away as H2, eventually making H2 gas. So the picture he had was that there's sort of two free energy curves at a given overpotential, which correspond to kind of moving the ion, which is here the proton, but not transferring the electron. And the electron will transfer kind of where I've indicated this little orange explosion, which is when those two cross, is that you're kind of stuck in the reduced state, and then you have a fluctuation also of the oxidized state, and when the two are the same, that's when the transition happens. That is, in fact, the same insight that Marcus had actually 30 years later. And it's in this paper, in both these papers, actually, quite early on. What they were missing, though, is actually what happens at that little orange explosion. He did have a theory, though. It's an amazing paper because what he said is he actually calculated sort of as a function of overpotential, he intersected those curves, said there's a barrier, and then he wrote down the quantum tunneling formula in the WKB approximation that had just been published like 2 years earlier. So it's a really innovative paper, but that's not actually how we think about the electron transfer part of it. But this integral over electronic states of sort of a fundamental transition probability is exactly what I'll be coming back to. Now, I mentioned Marcus. So Marcus is considered to be the father of quantum electrochemistry, and he began publishing very influential foundational papers in this field in 1956. Going to the 1960s, he then was actually awarded the Nobel Prize in Chemistry in 1992 for electron transfer theory. And so the basic insight that Marcus had, which again is similar to Gurnie's insight, is that electrons do not transition like classical objects diffusing over a barrier, dropping down on the other side like little tennis balls or something. They're quantum mechanical. They have a certain set of allowable states, and when there's more than one state they can be in, they can hybridize, but they have to be at the same energy. So as Marcus said, electron transfer is isoenergetic in the dark, meaning like you could have a photon come in and kick it to some other state, but if it's in the dark, it can't change, it doesn't diffuse to some higher energy and come back down. So what actually happens is the environment, so the atomic positions rearrange in such a way that the available energies and the orbitals that go with them are constantly changing, and when the electron is going to jump from here to here, it's the environment or the solvation structure that is fluctuating, and only when you have the same sort of energy available or something close to it can you have a transition. And if you apply Fermi's golden rule for transitions, and you make the key assumption that Marcus did, which was not done before, is to say, well, the donor acceptor states in some reaction coordinate, which can be defined in a few ways, as I'll talk about. He said if you're fluctuating around a minimum, it should be parabolic. So where he found the barrier was not by intersecting two linear curves, by intersecting two parabolas, basically. So you say, the electron will transfer, for example, in this reaction coordinate here. Now, what is that coordinate? It could be, for example, that he has a electrostatic theory that says there's a solvation structure, which is a sphere around the ion, and there is a change from the static to the optical dielectric constant. So the electrostatic properties change in such a way as to facilitate transfer. It can also be phonons or stretching of bonds that can lead you to following these parabolas here. And an important prediction of this theory, which already Marcus made in 1956, is that if you kind of tilt one of these relative to the other, so you have a driving force for the reaction here written as delta G, you can get into the so-called inverted region where the barrier actually goes to zero and then it starts to grow again kind of on the other side. What that's saying is you kind of have to fluctuate, like this blue curve has to fluctuate kind of in the wrong direction to sort of find its way back down again. What it's also predicting is that the rate now, instead of having an exponential dependence on a barrier over kT, it's actually something more like a parabolic dependence on the driving force, which is quite surprising. It's like an upside down parabola. So what it's saying is that as you increase the driving force for the reaction delta G, first the rate goes up, and then it goes down, actually. And there's a maximum. And also the theory provides certain approximations can give you even sort of what the prefactor is quantum mechanically. Now, to take this formula, which is mainly used for electron transfer in just a bulk system, for example, electron hopping from one site to another in a liquid or moving along a molecule. If you want to go to an electrode, you have to basically do what Gurnie did, is you have to write delta G is the given by the electron energy. You have to integrate over all the electron energies relative to the Fermi level. And then you also bias the Fermi level with the so-called formal overpotential. Okay, so that's not shown here. So this is actually quite a successful theory. On the other hand, it really has almost not been used in electrochemistry, and this is something that's been bothering me my whole career. Actually, like why don't we use Marcus theory actually, or hardly anybody does. And for that matter, where does the Butler-Volmer equation come from? It's got to be somehow related to this. But it's not actually so obvious. But what I would say at a fundamental level, what is missing here is bond breaking, or maybe more generally ion transfer. Because in electrochemistry, we don't really care about electrons transferring by themselves. We want electrons transferring and causing or being associated with a chemical transformation. That's really the key. And so that's, I think, where there's still room for some more theory. Now, in chemistry, since the time of the Nobel Prize, and starting in 1994, actually there's been quite a bit of work on a particular type of theory of the type that I'm going to be describing to you, which is called proton-coupled electron transfer, or PCT. Theory goes by a number of other names as well, and there's different flavors. But essentially, it's sort of a double Marcus theory, where they say the proton is also a quantum mechanical object, just like the electron, and there's a second coordinate, so it's kind of like a coordinate for electron transfer, another one for proton transfer, each of which has to do with fluctuations of the environment, changing those states. And people have used quantum simulations to even predict some of these quantities and calculate these parabolas and actually get rates. So you can see here, for example, from this work of Sharon Hamas-Schiffer, here's the rate constant now written as a double integral sort of over the electron states, electron energies, and also the proton vibrational energies in the environment as a function of the driving force. So in principle, you can predict rates that way. But as I state here at the bottom, I think one reason this theory still isn't really used in electrochemical engineering, and maybe still, I think, could be improved upon in terms of just the understanding and application, is that it's still pretty complicated. It doesn't lead to a simple formula, and it doesn't also agree with a lot of experimental measurements, at least not directly. Now, in particular, that theory cannot explain Taffel's law. Now, we can debate whether Taffel's law actually is seen in experiments or not. It's not always seen, as I'll show you later. But I showed you Taffel's original data, so at least sometimes it's seen. And actually, as Bakris pointed out in his book, he says all quantum mechanical formulations of electron transfer, basically building on Marcus theories, have an Achilles heel that they cannot replicate Taffel's law. And he says it's one of the most tested and verified laws of nature. I'm not sure I would go that far. But certainly there is evidence for Taffel's law, certainly for hydrogen evolution. It's pretty reasonable. And so I state here that despite Nobel Prizes for electron transfer, also for quantum chemical simulations, density functional theory, we still can't explain Taffel's law, and I would argue that we still don't even really have a very predictive framework for predicting electrochemical reaction rates. And in electrochemistry, all the actions of the interface. We've heard about ion transfer or ion motion in the bulk and double layers. Those are definitely important. But the most important thing is actually the reaction at the interface. And that's the one thing we don't understand very well. And so that's what I've been focusing on for the last more than 10 years now. Originally in the field of batteries, mainly in the field of batteries, but I'll come to other examples as well. So I got into this somewhat circuitously. I was teaching Marcus theory in my electrochemistry class and also teaching batteries. And I had a very talented student who's now a professor at Washington University in St. Louis, Peng Bai. And we were working on a battery material called lithium iron phosphate, which is actually a very important material for batteries. You may know that it's one of the popular materials for electric vehicles, and pretty soon will probably be the #1 material. It already is the main material used for cathodes in China and slowly elsewhere as well. It has a lot of nice properties. But for today's talk, the interesting thing about lithium iron phosphate is that it's an electrical insulator. So when John Goodenough, Nobel Prize winner for lithium-ion batteries, when he wrote the first paper on LFP, which was in 1997, the last paragraph of the paper says it's a great material, it's earth-abundant elements, low cost, non-toxic, safe, but not good for high power, only for low power applications. That's what he was able to get. One reason for that is it's an electrical insulator. So you can't really make a good electrode out of something that doesn't conduct electricity very well. But what happened next, though, is within a couple years, people ball milled the particles to be really small, definitely submicron, maybe 100 to 300 nanometer type scale is typical. And they carbon coated the particles so they could get electrons very easily to a high surface area. And then it went from being a terrible, slow material to actually being one of the fastest materials, which at the time, it was LFP that took us from the electric screwdriver to the electric drill that you could hold in your hand. It was battery operated. And then it also can be used for electric vehicles. So that's a pretty interesting kind of reversal of fortune, if you will. So what Peng set out to do was to see if maybe actually LFP has electron transfer limited reactions. So when people think about lithium-ion batteries, the reason we call it a lithium-ion battery is lithium ion goes into a host solid material, and it's still lithium-ion. It doesn't get reduced. We're not making a lithium metal. So you might ask, where is the electrochemistry happening? Because as I said, electrochemistry starts with electrons. What's actually happening is that as the ion goes in, you're reducing the material. Not the ion, but something nearby. Typically in battery cathode materials, it's a transition metal, like in this case, iron. So iron's going from +3 to +2 oxidation state as the lithium ion is going in. And what Peng and I worked on here was the hypothesis that maybe the rate limiting step is actually not the ion transfer, but it's actually electron transfer, in this case from the carbon coating, which is essentially a metallic state, to the iron. And so now LFP, as some of you may know, has all other interesting phenomena, which I won't talk about so much today, like phase transformations. And so we had to deal with that, but we devised an experimental method by basically taking small pulses of potential and seeing how the current sort of rises and falls, and we modeled the rising part of the current as nucleation and the falling part as reaction limited, and that way we measured and inferred reaction kinetics, assuming we were reaction limited in our experiments, and basically plotted here the log of the rate constant against the overpotential. Nice thing about LFP also, it has a very flat voltage plateau, so you know exactly where equilibrium is, and so you can kind of more easily measure what is the overpotential actually. Anyway, plotted all this data, and amazingly, it was like a perfect fit to Marcus theory, actually. So we were kind of blown away by this. The lambda, or the organization energy, controls the curvature of the Tafel plot. So basically, if you plot log of current versus overpotential, it's curved, and it's not Tafel's law. And it's a perfect fit. Now, this is Marcus theory for a metallic electrode. So what you see here is the rate constant is the integral of the Marcus rate, which, as I showed you earlier, where the delta G is now basically an integral over the x here is the electron energy. So this is this kind of Gaussian dependence I talked about earlier, and this is the Fermi distribution. So this is the kind of integral you have to do to express the rate, and that's the curve that's shown here. So it was like a beautiful fit, actually. It was kind of surprising. And not only that, I mentioned that Marcus in 1956 had published a very simple electrostatic estimate of lambda, the organization energy, and it's shown right here for so-called outer sphere reactions. And this would be cases where the region where electron transfer is happening is sort of very far from where it starts. The donor acceptor are kind of like not too strongly coupled, okay? And if you basically plug in the optical and static dielectric constants of LFP, actually, and then also from the crystallography, the distance for electron transfer and the size of the iron site, this lambda was almost a perfect fit for what we got from experiments. So that was kind of nice. Even with that, the reviewers didn't like it. It was very hard to publish this paper. And we finally got it in because we varied the temperature. And in Marcus theory, lambda is an energy. It's not a free energy. It's an energy. So it shouldn't depend on temperature. So these curved Tafel plots have the same curvature as you vary temperature. And I'll come back to that later, and I'll show you that that was actually true to pretty high accuracy, actually. And that was really what got us through. Now, why is that important? Because it's not like experimentalists haven't seen this before. They see this kind of thing all the time. Like I said, Tafel plots are always curved. The thing is, they straighten them. How do they do that? Because if you take Butler-Volmer equation and you put it in series with a resistor, and you call that a film resistance, people will say, oh, there's the reaction, but before it reacts, it has to go through some kind of film, some kind of resistor. Well, if you fit a film resistance, you can take any curved Tafel plot and eventually straighten it. And you can get it as straight as you want by making it even a voltage-dependent film resistance. So it's kind of like a mathematical trick. And the more you dig, you start to realize actually people are not actually seeing the Butler-Volmer equation in most cases where they say they do. It's because they're doing that kind of fitting. So I'll come back to that again, but the important thing is that a film resistance, whatever it is, should be temperature dependent. So that was our argument here, is that basically in Marcus theory, though, lambda is actually not temperature dependent. Okay, So that was the starting point. But then years later, the next kind of breakthrough here was thinking about really kind of motivated by the proton-coupled electron transfer theory. This was with my student Dimitrios, who's now a professor at Princeton. By the way, there's 4 students who worked on this. They're all professors now, and it's taken a long time to work on this. So like, it's really been quite a journey, actually, on this particular topic. And so the picture that we developed here, coming right from CPT theory, is that we have this Marcus reorganization coordinate that I talked about before that really kind of controls electron transfer, but that there's also a collective variable in this direction, which is, I'm now giving credit to Gurnie, actually, and Butler for first formulating that kind of way of thinking, that basically the position of an ion, in this case, think of like the lithium ion being inserted, is, or some collective variable associated with the movement of an ion, like for example, you're breaking a bond in some molecule, is that this, and we treat this coordinate classically, and this coordinate is more quantum mechanical. And so that's kind of the difference here. In CPT theory, they treat both quantum mechanically, so essentially it's parabolas in this direction too, and they also do quantum simulations as well. So anyway, so this is the picture, and we basically did Marcus's approximation of parabolas in this coordinate, but not in the other coordinate, and I'll come back to different pictures there. And the idea is the barrier is somewhere in the middle. It's typically going to be a coupled process. And this paper here that came even a couple years after that is where I tied it all together in what I call unified theory, because it actually does unify Butler-Volmer and Marcus. So I'm going to come back to this. So first of all, there's sort of, at the simplest level, kind of 2 basic energies that come in. In the electron transfer direction, there's this, what I call lambda, the reorganization energy. What that is if I were to sort of reorganize the solvent to sort of the new configuration for the accepted, let's say the oxidized to the reduced state, but don't transfer electron, that's lambda, okay? So it's basic, if you kind of follow one of these parabolas to where the other basin is, that's lambda. And if lambda is big compared to whatever's happening in the ion transfer direction, so there's some beta, which is like a free energy of ion transfer without electron transfer, and if that's much smaller, then you have the landscape looks something like this. So if you kind of view from the electron transfer direction, it's basically just Marcus theory, but there is a bit of a correction from what's happening in this ion transfer coordinate, which I'll come back to later. Another actually important thing that I've worked on in this field also, that from a practical point of view, is that this thing I've written down here is actually a very accurate closed form approximation of the Marcus integral. So I showed you this thing. You know, no electrochemist wants to work with this. It's an indefinite integral. I don't even know what it looks like until I start plotting it numerically. But what we did is in that paper, one paper with one of my math students, we took the large lambda limit, small lambda limit with asymptotic approximation of integrals. We matched it and got like very high accuracy for all values of the parameters, actually. So that's what this formula is here, actually. So this is just another way of writing kind of Marcus kinetics. But there's something new, though, which is that actually there is so in the prefactor here is an ion transfer barrier. So even when you see a process that looks like Marcus kinetics, there is still a sign that there is kind of an ion transfer or bond breaking going on in the temperature dependence. So I'll come back to that. But what I was actually most excited about here in this particular work here was kind of realizing that the Butler-Volmer equation is in here too, and it goes back to Gurnie and Butler, because if now we say that the betas, like for reduction oxidation, those free energies of ion transfer are bigger than lambda. So now these sort of parabolas in the sort of electron transfer direction are small. Now the energy landscapes look like this. And so if you kind of view now from the ion transfer coordinate, this looks just like the Gurnie-Butler thing I was showing you, except where I drew this little orange explosion, it's basically Marcus theory kind of into the page. And that then gives you a nice expression for the quantum mechanical ion transfer would happen when the ions have moved to that position where they're nearly isoenergetic. So what's nice about this theory is you can get the Butler-Volmer equation. By the way, to do that, you have to assume that the ion transfer direction, the diabatic surfaces have a roughly linear dependence on the ion transfer coordinate. You will then get Butler-Volmer equation. But what's nice is you get the prefactor in terms of quantum mechanical things, actually. So I'll show you later the Fermi energy of metal is there. You've got the lambda, the organization energy is there. And there's also a barrier for ion-coupled electron transfer, as I call it, which involves not only the betas, but also the lambdas. So there's kind of a prediction of what the barrier would be. So it's basically Butler-Volmer equation, but now with everything predicted in terms of microscopic quantities, which in principle could be computed. So I'll come back to that. Now, also another nice, I think, mathematical contribution in this paper is to kind of go back and do some of that asymptotic analysis that I'd done in the earlier paper for Marcus theory for the full coupled theory. So if you take like a general energy landscape like this, you know, many different kind of dependencies are possible on overpotential, temperature, and composition in the reaction rate. But if you make a simple assumption that it's linear in one direction and parabolic in the other direction, then you can actually do all the integrals with the Fermi distribution and all that, and you can get a formula, and I'll show it to you on the next page. But what's nice about it, though, is if you make a Tafel plot now of the log of current versus the formal overpotential, you kind of have this transition from Tafel's law, which is when the beta is larger than lambda, so ion transfer is the slower, more rate-limiting process, to the opposite case of a certain kind of curved Tafel plot when it's the opposite, when the electron transfer is rate-limiting. And then when they're both limiting, you get something, you know, kind of in between. And another interesting prediction of the theory is for within certain approximations, you get a limiting current, actually, for this is when you have a wideband approximation for a metallic electrode, and you assume that the electronic coupling is independent over potential. Anyway, so so this is the structure. And actually, I was just presenting this work. I had the great privilege of presenting this at the inaugural workshop of the Marcus Center for Theoretical Electrochemistry at Caltech just a few weeks ago, actually, in July. And I was amazed that Marcus was actually there. He's 102 years old. And not only that, he attended the conference for 2 straight days sitting in the front row, just something just like this, and there weren't all these cushy breaks, and it was like just talks. It was like all his former students, and you know, it was just talk after talk with like a lunch break, and he was there, so it was amazing. And in fact, he was very alert. I went to introduce myself to him. I'd only met him once before in person, but we had a bunch of emails maybe 15 years ago. He recognized me, and what he said was, "Oh, I remember you. We believe in curvature." What he meant is Tafel curvature, because every electrochemist will tell you, no, Tafel's law is straight. And he says, no, it's got to be curved. So on the other hand, I did acknowledge at least Bakris here and many other electrochemists to say, well, it depends on the situation. There will be curved Tafel plots, and some of them may be kind of straight, and it depends actually whether ion transfer or electron transfer is the rate-limiting process, actually, in this more general theory. So that's kind of the whole picture. And interesting now, let's go back and look at Tafel's data itself, actually. So I've kind of flipped it here so things are backwards, so it kind of matches my picture here. He actually plotted, he's flipped the 2 axes. So he had, anyway, what you see here is this is the replotted data from that other paper I showed you. So this is the log of current density versus overpotential for hydrogen evolution in acid. It's pretty straight, his actual data, but it does start to curve. And so this is because even in the cases where it's straight, you still hit this quantum mechanical limit. And what's happening there is when the overpotential is big enough to kind of tilt one barrier relative to the other one, eventually it's a barrierless transition, and it's entirely dominated by quantum. It's just basically quantum mechanics of jumping from one well to the next with no barrier, actually. And so that's, I think, what we're seeing. It's a little hint of right there in that particular data. By the way, since you guys are a lot of math people in the audience, this is what I call a simple formula. So if you just look at the oxidation rate constant, it's very similar for the reduction. You have sort of this 2-part formula here that is a decent approximation of this CIET rate when you have this kind of simple approximation of the free energy landscape. So, you know, Butler-Volmer equation, the difference of exponentials, this has some error functions in it, but it's still pretty simple. Like, it's just a formula. It's one line of code. If you do, you know, battery modeling, like you could actually just change this one line of your code. So let's talk about batteries now. So I just kind of overviewed the theory. This came from batteries, and we've actually applied it quite extensively with many wonderful collaborators to batteries, actually, lithium-ion batteries specifically. Now, as I said, I got into this by studying lithium iron phosphate, which is a very complex material, actually. So what's shown here on the left is basically a simulation of a single lithium iron phosphate platelet nanoparticle, which already my group was doing as of about 2012 with a certain equation I'll show you in the next slide. And I had a very hard time publishing these papers, by the way. And so interesting things are happening. So we, for example, used quantum simulations to find the surface energy of each phase. So their lithium iron phosphate likes to be either full or empty of lithium, more or less. There's two stable concentrations. Those are the black and the white. And it turns out the side facets, according to ab initio calculations, have a lower surface energy when they're wetted by the high density phase, and then the top surface actually prefers the low density phase. The second thing is the two phases have different crystallography. So when the lithium is inserted to the high density phase, the lattice unit cell expands in two directions and contracts in the third. And that leads to very complex mechanics. If a phase transition happens inside a particle, that's what you're seeing here, is that at first it nucleates on the boundaries, but now it's like a balloon being squeezed from the outside, and at some point it can't handle it, and it breaks into these stripes to minimize elastic energy, actually. So that's what we predicted. And when I was publishing these papers, my first paper, and this was rejected not by Science or Nature, but by Electrochemical Acta, one of the reviewers said, this is not electrochemistry. This was back in 2007. But now, actually, we've at least managed to convince some people. But the reason is that, thankfully, William Chu at Stanford, when he was a junior faculty member, kind of was intrigued by this and decided to use Stanford's synchrotron X-ray facilities to actually observe lithium iron phosphate nanoparticles. And Jung-Woo Lim was his postdoc, who published a paper in Science with us. He's now a professor in Seoul National University. And this blew me away, actually. These are actual images that they took of a particle looking like this, and keep in mind the simulation came first. Okay, so it takes a little while to scan a particle. You might only get 3 or 5 or 7 images, but it's pretty striking how similar these are. Now, this, though, on the right is a real particle. So this black thing is not an aberration of the optics. It's actually a hole in the particle. If you map it with SEM, you'll see there's actually a hole. And so there's a lot of sort of messy heterogeneity on this particle, but nevertheless, there's quite a similarity. And long story short, I could give a whole talk just on this, but it led to getting a very nice grant from the Toyota Research Institute for a center we call D3BAT for Data-Driven Design of Rechargeable Batteries. We kind of did some of the first work on battery informatics, machine learning, stuff like that. For this talk, what's interesting that we did, I think, is that we actually took these kinds of images and asked the question, can we learn the physics from it, actually? And I think we were among the first to do that, actually, at least in this context. So for that particular set of images, what I'm going to show you here on the top is just experimental data. It turns out, I think that for that particular particle, we had 7 images total. And we just make a movie to sort of continuously vary the colors. So we only have those 7 images. And then here is a PDE that we solve. And this actually is dc/dt. We did write down Butler-Volmer equation, which is this hyperbolic sine thing. But the thing is, we never get to large overpotentials. So this is not testing the overpotential dependence, but it is testing concentration dependence, because the concentrations are changing a lot. So here you see this exchange current as a function of concentration. Here's the thermodynamics, which is like a double weld function that says what the homogeneous free energy is as a function of concentration, where there's these 2 minima that correspond to stable phases. Also, there's the elastic effect that I mentioned. We don't fit that. We took the misfit strain from X-ray diffraction measurements and the elastic constants of the material from ab initio quantum calculations, which are pretty accurate for that sort of thing. So we didn't fit that, actually. So we just fitted these 3 functions. And actually, I should show you that we can get them to match pretty well. And in fact, let me show you how well it matches, actually. So the bottom is literally solving this PDE. And this is the experiment, actually. And so it's pretty hard even to tell the difference to the naked eye. And to make it this, we can do pretty well. I don't show it here just with that equation, nothing more. But there's one little trick here. Is we put an f of x out front. We said this is a model, by the way, with no diffusion. We're just assuming it's entirely reaction limited. By the way, I should have mentioned the active facet of the crystal is what we're looking at. It's the B facet of the crystal. Lithium iron phosphate crystal structure has kind of these 1D channels, and lithium can only go in on that facet. So you're kind of looking down on a surface, basically, and seeing how it reacts. So it's very convenient that way. Anyway, we inferred, just by looking at the dynamics, we inferred a rate constant map. And then actually, the experimentalists went back and checked that in fact the carbon coating thickness varies in a way that is consistent with our inferred variation of the reaction rate. I mentioned earlier lithium iron phosphate doesn't work with our carbon coating, and it turns out carbon coatings are actually not uniform. They can vary in thickness by a factor of 5 or so, maybe more, depending on the situation. The way it's actually made in industry, you basically take the powder, grind it down, and then you melt sugar on it, basically. And that ends up forming a nice carbon coating. So it's not really high tech, and it's pretty heterogeneous, it turns out. And we showed that even on a single particle, there can be about a factor of 3 or 5 variation in the rate. Now, the important thing here is actually that, and this was published in Nature a couple years ago, and the lead author was my student Hongbo Zhao, who, by the way, is not far from here, professor at University of California, San Diego in chemistry and physics. And what we did is we looked at a large number of particles. So we had a total of about almost 200,000 pixels of data from 63 particles. And here you see left and right. Left is the experimental situation, which is snapshots of the particle kind of stitched into a movie. And on the right is the learned simulation, and every one of these is solving the same equation. It's the same free energy function and the same reaction kinetics for all particles. However, we learn the rate constant map from the heterogeneity differently for each particle. That's unique. And the thing spinning around here is the clock, because we can do experiments where we basically put lithium in, take lithium out, put it in, take it out, and you can do it for many particles. So that's the data set. And the important thing for this talk is what we learned from that. So we did learn something about the thermodynamics instead of this model here, which is the regular solution model that we and many other people have used. We got something a little bit more squashed here, which is kind of interesting. But what I want to focus on is that the exchange current versus concentration has a certain shape. And this is the expression from, if I take the CIET formula that I showed earlier, which is sort of the Marcus limit where you have electron transfer limited, and you take the lambda that I measured with Peng in 2014, no fitting, except for to rescale the curve. The shape of this curve is the dashed line, and the black is the average, is basically what came out of the learning from the images, and it's a pretty good fit, and it's different from what everyone uses in the battery field, which is the square root of C1 minus C, which is actually quite different near 1, and it has certain implications for dynamics of batteries. But anyway, so this is at least one nice confirmation. Now, another thing that was explained here, and in the theory that I showed, is that in the original paper with Peng, I mentioned we varied temperature. And sure enough, as you can see in the data here, these are different temperatures, 30 up to 50 degrees C, and the lambda was almost exactly the same every time, like very high accuracy, actually, which was one of the convincing things. But what we weren't able to explain at the time was the activation energy. So if you make an Arrhenius plot of the log of the rate constant versus 1 over temperature, the slope is the activation energy. So in Marcus theory, if it's symmetric, it should be lambda over 4. But the actual barrier we got was like significantly larger than that. And so now we understand what was missing is that part of the barrier is actually from ion transfer. It's not a pure electron transfer process. The ion also has to be transferred, and it's the ion transfer energy that was missing, actually, which we infer here to be about, in this case, 120 millielectron volts. So since that paper and others, actually, we just published, actually, last week, a paper in Science with my colleague Yang Shahorn was the lead author, well, she never co-corresponding authors, but her student Yirui Zhang did a lot of measurements. She studied about 50 plus, more than 50 different systems, different electromaterials, different electrolytes, different temperatures, and basically showed that we could collapse all the data reasonably well, actually, with the CIET theory, including both the sort of concentration dependence in the solid, sort of the filling fraction of lithium, and also the orbitpotential. Again, see the curved Tafel plot. Like, again, I could straighten that Tafel plot. We showed that here, by the way. Butler-Volmer doesn't fit well at all. This BIC here is a Bayesian information criterion, so we use Bayesian analysis to say what's the best model. Because if you have enough parameters, you can fit something. That's why I'm never like that convinced when someone tells you, oh, I fit experimental data. Well, what was your model? What were you fitting? You know, so the thing is with Butler-Volmer, you can only fit this data if every single data set you have a different series resistance. And there's no theory of that. You have to fit it. So that's a lot of parameters. And so the Butler-Volmer equation can fit this data when you have a series resistance added, but it does so with lots of sort of arbitrary fitting, and so it's not, it's from in a Bayesian sense, it's not the best model to select compared to the CIET theory, which actually does it with many fewer parameters. So at least within the battery field, it's becoming recognized that electron transfer actually can be rate limiting in lithium-ion batteries, and that sort of the Butler-Volmer equation should be replaced or modified. What's also exciting is the possibility now of doing quantum simulations to predict the reaction rate from first principles. So the first paper to do that is this one in 2024. I do think a lot of improvements are possible on what was done in this paper. But it's a nice paper because it's first. So I am a co-author on this, but I'm somewhere in the middle because I didn't have a lot of control over this study. It was Yang Shahorn's collaborator at NASA who did the study, so I had some influence. But so I think more needs to be done here. I'll point to some of the specific things. But basically, Joachim Stenlid and collaborators, and Stenlid is now, by the way, also a professor in Sweden. I should have added that. So looked at lithium cobalt oxide. That's one of the most common, it is the most common cathode material for portable electronics. Like your cell phones, basically, and your laptops, these are generally lithium cobalt oxide. And in the electrolyte that we use here, which was a certain organic solvent with various lithium salts in it, he did kind of classical molecular dynamics simulations to try to figure out like what are the typical solvation structures for lithium, and also what it turns out there's 3 different sites on that particular plane of the surface where lithium could intercalate, and sort of repeated the calculation for each possible site and viewed those as parallel pathways. And so there's a couple steps. So first you need to know, kind of given the activity of lithium in the bulk, what's the coverage or probability of finding lithium at the surface? And then once it's there, you need to know kind of what is the solvation structure around it. And then you do that calculation that is shown in this plot here, where you basically pull the lithium in or pull it out without electron transfer. So basically what they did there was using a method called constrained density functional theory. So it's basically a DFT quantum calculation. Okay, perfect. It's a DFT quantum calculation where you constrain some electron density. So what they did here is they said, let's actually put an extra electron on one of the cobalts, actually, which is roughly what's happening here. Although that's where I think more work needs to be done, because the way that was done might not be exactly constraining the electron in the right way for this particular material. But that's, in the case of iron phosphate, it'd be easier. You definitely want to put the extra electron on the iron. Anyway, so basically this is what you get when you sort of pull the ion in or pull it out without allowing electron to transfer, so you can get kind of those beta parameters that were in the theory. So what they were able to show here was especially this, is that the lambda organizational energy that came out of it was very close to what we measured experimentally for these materials. This was for lithium cobalt oxide. It's around 0.1 volts. And also it had a dependence on the electrolyte that was also captured. The formula, as I show here, was basically you took the CIT expression that I showed you, but we weighed it over 3 equivalent sites on the LCO surface as if they were kind of parallel reaction channels. And each one has a different probability of occurring, having to do with this delta omega. That's the absorption free energy to the surface. So basically, it's like a Boltzmann factor saying what's the probability of finding a lithium at that site, and you have to add over all the different sites on the surface, and you get the rate. Bottom line is that here they actually took the experimental data from that Science paper. And by the way, you can see how long it took us to fight with the reviewers for Science, because this was published in 2024, more than a year before the Science paper was actually published. But we had the data provided for this paper. And so all that was done here is to fit one parameter. So this is really an ab initio prediction of a reaction rate from quantum first principles. So the one parameter is the active area or number of active sites, because in the end we make a very thin porous electrode. We try to operate it under reaction limited conditions, and we can estimate from like BET analysis or things like that what's the active area, but it's pretty hard to exactly count the number of active sites. We fit basically an overall prefactor, okay? But aside from that, though, if you fit, say, this top blue data here, and then you vary X, which is the filling fraction of lithium and cobalt oxide, and then you also change the anion from chlorate to PF6, you can see that this is all just captured by the model. So there's no other fitting. Just one number is fitted to capture all this data reasonably well. It is on a log scale, so admittedly this is not like perfect match here, but at least the trend is in the right direction. And I think this is very promising, because you're probably familiar with the transformative impact of things like the efforts like the Materials Genome Project. What do? They take bulk materials like crystals, they put atoms in different places, and they compute the bulk properties. For example, the diffusivity, thermal properties, et cetera. And we know how to do that for bulk materials, especially bulk crystals. And we even kind of know how to do it for liquids, but we don't know how to do it for interfacial reactions. So today we cannot just like start a computer off calculating, how do we optimize this interface, like what electrolyte should I choose, what coating should I put on to get a fast reaction that I want, or how to kill a reaction I don't want. So I think the possibility of having a theoretical framework can be really transformative in this field. I'd like to leave you in the remaining 5 minutes with just a little bit of a taste of other applications. So this theory kind of came from batteries, and that's where it's been most tested, but actually there's now quite a literature building in other cases. My group is also looking at it in electrocatalysis, electrodeposition, and even other problems. I won't go into a lot of detail here, but just to show for electrodeposition, people do see curved Tafel plots, which again are best explained by sort of electron transfer limited reactions. And one interesting example here is actually the morphology of lithium peroxide electrodeposition in a lithium-air batteries actually was connected to solvent properties through the reorganization energy through this theory. So that's one interesting tidbit there. I think that what I want to maybe leave you with here is just the last examples here, coming right back to the beginning of my talk. So I mentioned electrochemical kinetics, the field kind of started with Tafel's paper, 1905, on hydrogen evolution in acid. Believe it or not, after more than a century work, we still don't really understand hydrogen evolution in acid that well. Some people will get mad at me if I say that, but I think it's true. And what I mean is we don't really have a really molecular level understanding of what's going on. And in particular, there are certain trends that have been noticed and I believe not properly explained. One of them is this Bockris, the same Bockris I mentioned earlier, already in the 1940s noticed that there's a pretty strong trend. This is a collapse of data here I'll explain in just a moment, but basically if you plot the hydrogen evolution reaction rate versus the metal Wurf function, there's a pretty nice dependence, sort of an Arrhenius dependence. So it's log of the rate versus the metal work function. That wasn't really explained. And if you, and basically starting around the time of Trasadi's paper, he kind of acknowledged this, but he said, no, the way we should think about electrocatalysis instead is that don't plot it against metal work function, plot it against the metal hydrogen bond strength, which is not that well understood, and there's kind of issues here, and make what's called so-called volcano plot. And so you may know platinum is the best catalyst for this and many other reactions. And so by this way of thinking, which is really the ingrained way of thinking right now, people say, what's special about platinum? It's because it absorbs hydrogen perfectly. It's like at the top of this volcano. Okay, now first of all, I'm a simple guy. I'm a physicist. I like straight lines. Straight lines I know are good fits. Like when you show me a bunch of clusters and you say it's a volcano, I don't know if I see that really, but okay. Over here, this is data taken from Trasadi's paper. And basically, if you plot so let me back up a little bit here. So we know that hydrogen evolution from Tafel's work and onward is a reasonably good fit to Tafel's law. So with the Butler-Volmer equation is a reasonable model here. It's not such a good model for the batteries, but it should work here. If you go through the theory that leads to Butler-Volmer, and you keep track of the metal itself, actually, relative to the working electrode. So for example, in this field, potentials are measured relative to the standard hydrogen electrode, which is platinum doing hydrogen evolution in acid. If your other electrode is gold or ruthenium or some other material, then there's a change in Fermi level between the reference electrode. There's also a change in so-called surface potential, which has to do with sort of the orientation of the solvent on the surface and whether it's pulling electron density on or off. This is a very old concept in electrochemistry. But basically, if you kind of look at the theory, it actually has this red term here which predicts, in the case where you have Butler-Volmer kinetics, that the exchange current has exactly this exponential dependence on the change in Fermi level, which is pretty close to the change in the work function. Work function is if you basically hit the metal with a photon, it kicks off an electron into vacuum, like what is the energy? That's roughly the Fermi level. And what's special about platinum is not necessarily it's at the top of this volcano, it's that it has the lowest Fermi level. So platinum loves electrons. Now why is it so good for catalysis? Is because relative to the other electrode, if you have a low Fermi level, you're sucking electron density from the other side, which gives you more electrons to react. So even though the electrons are very happy on platinum, they still want to be there versus the reference electrode more than on some other metal. If you have gold, then the electrons say, no, I'd rather be on the platinum on the other side. So that's actually part of the explanation here. And I should acknowledge that realizing the importance of work function, I learned from this beautiful paper of Buckley and Leddy, which didn't have a quantum theory, but had kind of a nice Butler-Volmer based analysis of the effect of metal work function. One last thing, I'll just real quick here, just to show you, like, this is kind of interesting now. In the batteries, people have kind of accepted these ideas. In electric catalysis, it's like, again, starting to be a struggle, but we're learning some interesting things. So if you look at Tafel plots for, like, this is CO2 reduction in water, they look pretty curved, actually, but people always interpret this to say, oh, that's like diffusion limitation or some film resistance, and they'll fit that. So essentially what they're doing is keeping Butler-Volmer, and they're straightening it, okay? But the data is pretty flat, and especially some of the data is like extremely flat, which kind of wouldn't happen if you just had a resistor there. Anyway, I have this paper from a few years ago we put on Chem Archive. It was with my colleague Fakila Bruchetta, one of his students who was about to graduate. They did some experiments, took some literature data, and basically did that same Bayesian analysis and actually showed that the Marcus theory actually fit this better than Butler-Volmer by itself, even with film resistance fitted. The paper was rejected. The reviewers killed it. They said this is ridiculous. First of all, it's an inner sphere reaction. It couldn't possibly obey this particular version of Marcus theory. Can't possibly be right. So this student graduated. It wasn't my student. My colleague Fick is an experimentalist, so we said, okay, forget it. This is too much trouble. But then I noticed actually that other people read this Chem Archive preprint, including this group at Berkeley of Bell and Weber, and actually found that it really fit their data quite well for carbon dioxide reduction in real devices, actually, in electrolyzers, and showed that it worked better in Butler-Volmer. This was just published last year in Nature Chemical Engineering. There's a few other papers, too. And interesting thing is that now we've come back to this. So I actually now have a student doing quantum simulations now of electric catalysis. So we're basically bringing the carbon dioxide molecule near the surface and doing the constrained DFT calculations, also accounting for finite temperature effects of entropy in the molecular environment. And this is in collaboration with Troy Van Voorhis, my colleague in chemistry. And long story short, we do kind of see this kind of nice CIET-like landscape for CO2 reduction. If you kind of take a look at it from the side, you have these two curves, and where they cross is where the reaction happens. And if we take our measured, ab initio predicted quantities, we actually can predict the experimental data for CO2 pretty well. But an interesting thing, which is on the next slide here, is that this is a technical point, and this is my last slide. Sorry, I can stop here, but. So the reviewer said it can't possibly work here because the inner sphere, so a strongly coupled system. Here's an interesting mathematical fact. If you take these two parabolas and you now say, like in quantum mechanics, electron can be in two states at the same time, so you can basically have hybrid like bonding, anti-bonding orbitals. You can find the eigenvalues of the Hamiltonian matrix. So that leads to basically a lowering of the barrier, basically, if you can be sort of, and that's so-called adiabatic electrotransfer. What we found is that actually, even when it's strongly adiabatic, it's a mathematical trick. If you redefine lambda this way, it's kind of like still two parabolas intersecting, but they're different parabolas. And for CO2 reduction, the experiments say lambda is 0.75 from Dan Nasser at Harvard for CO2 reduction. But ab initio calculations have said it's super high. It's like 6.3, actually. So like this seemed like, again, like it can't possibly be right that you can apply Marcus theory. But the point is you have to use this correction. The coupling is very strong, actually. And so it turns out that actually it might be quantitatively consistent. Anyway, so I'll just leave you with that just to show that basically this is, I think, a general framework for electrochemical reaction rates. You can use it in your mathematical models for whatever system you want to look at. And I think in a number of different fields, we're beginning to really connect this to quantum first principles and make ab initio predictions of reaction rates. Thank you.